Hello. Hello. Can you hear me? Hello. Hello. Okay. So let us now begin today's lecture. So we will continue from where we left off in the lecture earlier this week. So uh, so we were discussing. Let us take a little step back and sort of go over the tail of the last lecture. So we were discussing this rather complicated mortgage problem. So suppose you have borrowed $100,000 at 6% annual interest rate and to be paid monthly over 25 years. So how much is your monthly payment and how much do you owe after 50 years? So again, as we have seen many times, it's often useful to sort of think of these problems in terms of in terms of um, uh, it's often useful to think of these problems in terms of general variables. So, so let us sort of put this problem in a more general context where instead of actual figures for the various quantities involved, we use symbols because that sometimes makes the makes the main mathematical ideas or issues involved very clear. So suppose you have borrowed $C at annual interest rate I and it is to be paid off monthly over n years. So in our context, C is 100,000. Annual interest rate I is 6% or in terms of fractions it is 0.06, paid monthly over n equal to 25 years. So you are interested in finding the monthly payment R. Okay. So in problem 2, so in this problem, as we already mentioned, C is 100,000, I is 6 over 100 or 0.06, and n is 25. We are asked to figure out R. So what is the monthly interest rate? In the last lecture we worked out the simple relationship between the monthly interest rate and the annual interest rate. So if the annual interest rate is I mean I is a fraction, so not in terms of percentage but in terms of a fraction. So if I is the annual interest rate, then after 1 year your fund, your debt or your investment will grow by a factor of 1 plus I. On the other hand, if the monthly interest rate is alpha, after 1 year the investment or the debt will grow by a factor of 1 plus I. And if the monthly interest rate is alpha, then after 1 month, your debt or your investment will grow by a factor of 1 plus alpha. Okay. Now this C times 1 plus alpha is what you start your second month with. So after 2 months, you will arrive at the starting amount, which is C times 1 plus alpha at the beginning of the second month, multiplied by another factor of 1 plus alpha. So you get 1 plus alpha to the power. So it's just the same idea being sort of recycled once again. So after 3 months, so the third month you begin with C times 1 plus alpha squared and you grow by a factor of 1 plus alpha. So you get you grow up to C times 1 plus alpha cubed. eventually after 12 months, which is 1 year, you grow to C times 1 plus alpha square to the power of 12, because there have been 12 months intervening. But the amount at the end of 1 year should be the same, irrespective of whether you express it in terms of months or in terms of annual interest rate. So the amount in terms of monthly interest rate should be equal to the amount in terms of the yearly interest rate or annual interest rate. So these equations should be true. So C and C get cancelled and you get yes. Okay. So what is our situation? So I for us is the annual interest rate. So it's 6% per annum, or in terms of a fraction it is 0.0, it's 6 over 100 or 0.06. So the right hand side of this equation is 1 plus 0.06 or 1. And the first quantity that we will figure out is the monthly interest rate, alpha. So we have to solve for 1 plus alpha to the power of 12 is equal to 1.66. So alpha is 1 plus 1.06 to the power of 1 over 12 minus 1. And if you do it with the calculator, you will get something very small like 0.004867. Okay. So this is one important ingredient of our problem, which is the monthly interest rate. Why is the monthly interest rate of interest to us? Because at the end of the day, we are asked to find the monthly payment, right? So you can imagine that the monthly payment would be closely related to the monthly interest rate. So that's why we go ahead and figure out the monthly interest rate first. So monthly interest rate for us is 0.004 blah blah blah. Okay. So now let us continue. So our actual goal is to find the monthly payment, monthly rate of payment, so that if you keep on paying this amount over every month over a period of 25 years, your loan gets repaid. Okay. So in order to calculate this, we will use the following device. So let's say that we start with C0 amount of debt, which is in our case is C, so it's 100,000. Okay. So let's see that. So at the end of 1 month, the following will happen. In 1 month, our debt will actually grow because of the monthly interest rate. But it will also reduce to some extent, because at the end of the month we are also paying off some amount. Okay. So our debt grows by a factor of 1 plus alpha. So it's 1 plus alpha times C0. But that amount is further reduced by an amount R, which is our monthly payment. So this is the net increase of our debt by in 1 month, or net amount owed. Let's say net amount owed after 1 month. Okay. So this is the C1 equal to 1 plus alpha times C0 minus R. So we can call it the net amount owed after 1 month. So it's like a competition between these two rates, so these two quantities. So your monthly debt is growing, and you are paying off some of it, so it's reducing by a bit. So it's like a race between these two factors, and you want to find your rate of monthly payment R such that exactly after 25 years, that is 25 into 12 months, these two quantities reach the same level, so that you owe 0 amount to the bank, after which your payments will stop. So that's the idea. So after 1 month, you owe the net amount C1 to the bank. Okay. So at the beginning of the second month, you start with amount C1, which you have to return to the bank. Because of the monthly interest rate, it grows by a factor of 1 plus alpha. but because of your monthly payment, it reduces by an amount of R. Okay. So at the end of the second month, you owe the bank 1 plus alpha times C1 minus R. Okay. So of course, C1 is a quantity which you have sort of cooked up for the convenience of your calculations. So let's go back and substitute C1 in terms of the original variables of the problem. So we use the previous equation, C1 is equal to 1 plus alpha times C0 minus R. So let's substitute it here. And you can simplify this to be C, which is C0 is the same as C. So this is C times 1 plus alpha squared because of this multiplication, minus R times 1 plus alpha because of that multiplication, minus R. Okay. So this is C2. So let's now keep on doing this. So the third month, you will start with owing amount C2 to the bank. At the end of the third month, this will have increased to 1 plus alpha times C2 because of the monthly interest rate, but it will decrease by an amount R because of your monthly payment at the end of the third month. So the amount, the net amount which you owe to the bank at the end of the third month is 1 plus alpha times C2 minus R. Let's now do the same thing, play the same game and substitute C2 in terms of the original variable. So this is C times 1 plus alpha square minus R times 1 plus alpha R. Okay. So you notice the similarity between the previous step and this step. So there is a formal similarity, right? So this is C times 1 plus alpha cubed minus R times 1 plus alpha squared minus R times 1 plus alpha minus R. Okay. So you see the trend. So first time it was 1 plus alpha times C minus R. Second time it's 1 plus alpha squared times C minus R times 1 plus alpha minus R. Third time the power of alpha adjacent to C has increased and you get these additional terms. So generally you start the kth month with amount Ck minus 1. Because of monthly interest rate, it increases to an amount by a factor of 1 plus alpha, but your net amount payable to the bank is reduced because of your monthly payment at the end of the month, which is R. So at the end of the kth month, you still owe the bank this amount, 1 plus alpha Ck equal to 1 plus alpha times Ck minus 1 minus R. Okay. And you just play the same game. So you keep on substituting and finally you will see that you get just the continuation of this formula. So if you are C3, you had a power of 3 on 1 plus alpha along with C0, which is here. So this is the same as C0. So with Ck you get a power of k on 1 plus alpha, and then you have R times this these powers. So you have R times 1 plus alpha squared plus 1 plus alpha plus 1, right? You can express it like this. So generally, so you start, if you look at the powers of 1 plus alpha here, you start with 1, which is the power of 0, and go up to 2, which is 3 minus 1. So in general for Ck, you start with the power of 0 on 1 plus alpha and go up to the power k minus 1, and there is the factor of R, like in the case of Ck. Okay. So you get this general expression. Okay, any questions? And now we identify, well, this sum as a geometric series like this with x equal to alpha 1 plus alpha. So, and it is known that if you have a geometric series like this, then you can, and when x is not equal to 1, you can write down the sum of the geometric series in a nice and compact formula like this. Okay. So let us now use this formula in our case. So in our case, you have x equal to 1 plus alpha and exactly this kind of sum. So you get the sum equal to 1 minus 1 plus alpha to the k minus 1 minus 1 plus alpha. So this is 1 minus 1 plus alpha to the k minus alpha. Okay. So so let us now substitute this geometric sum here. So this for Ck. So Ck is equal to 1 plus alpha to the k times C naught minus r times this geometric series. So this is 1 plus alpha to the k times C, because C and C naught are the same, minus this formula times r. Okay. So this is the net amount you owe the bank after k months, not years, right? And you want to pay off the debt after 25 years. So since we are thinking in terms of months, let us convert the 25 years into months. So in 25 into 12 months, so n here is 25. So in 25 into 12 months, or in the case of n years, in 12 times n months, you want to pay off the bank. That means that you do not want to have any money left to pay, any money still owing to the bank. In other words, after 12 times n months, you want the net amount which you owe to the bank to drop to 0, right? So in other words, but the net amount after 12 months is C. The net amount after 12 times n months is C of 12n. So you want this net amount after 12 times n months to be 0. So you want C of 12n to be 0. So you substitute k equal to 12n in this equation, and you set it the Ck to be 0 and solve for r when k is equal to 12n. Okay. So you solve this equation, and if you do the simplification, you will get this formula for r. And you can do a little bit further simplification on this, because you recall the simple relation that we had between the monthly interest rate and the yearly interest rate. So 1 plus alpha to the 12 is 1 plus I. So you can write this as, so you can substitute this here and get this is 1 plus I to the n times alpha times C divided by 1 plus I to the n. Okay. Any questions? Okay. So let us now put in the numerical values and see what is going on. So in the previous problem, in this current problem, we have C is 100,000. The interest rate is 6/100 annually, so 0.06. So alpha is 0.004847 and n is 25. So you just substitute your figures in here or in here, and you can, using your calculator, you can get the simple answer of r is equal to 634.63 dollars. Okay. Any questions? Okay. So the second part of the question involves how much you owe the bank after 15 years. So here again we will use the formula for the amount that the net amount that we owe the bank after k months, and use it with k equal to 12 times 15 months, which is 180 months. So Ck, the amount we owe the bank after k months, as we already saw in the previous slide, is given by this formula. So Ck will be C times 1 plus alpha to the k minus R times this quantity depending on alpha. Okay. So here it's a simple substitution exercise because C is given to us, it is 100,000. R is given to us, so R we just calculated in the previous slide, and K is 180 and alpha is, as we already noticed, is 0.004847. So if you combine all of these and substitute, you get the answer $57,575.55. That's the amount you owe after 15 years. Notice a very interesting fact. So, so you had taken as loan 100,000, and you are paying it off in 25 years, and 15 years is already beyond the halfway point. But you see that because of the interest, you still have more than half the money what you had taken originally to be repaid, although the time remaining is less than half the total. Okay. So this is because of the sort of the nonlinear growth of the interest and so on. Okay. So to relate it to the competition between the linear and exponential curves that we discussed in the last lecture. Any question? Okay. So let us go ahead and discuss a bit about annuities. So an annuity is a series of payments made at equal intervals. So examples of annuities are regular deposits to a savings account, monthly home mortgage payments, monthly insurance payments, and pension payments. So so one of the examples of this, so this is a definition that is taken from Wikipedia. Now one of the examples that we already saw is in the last example, the last problem that we worked out is that of a situation when you had taken mortgage and you are making payments at equal intervals, at interval of 1 month back to the bank or the financial institution in order to repay your loan. So that's one example of an annuity that we saw. Let's look at another example which is relevant for all of us. So so when you retire, you may give a sum of money, the principal C, to a financial institution, for example the CPF board, in exchange for receiving a monthly income for the rest of your life. So this is a very similar image. This is a very similar situation or a mirror image of the mortgage problem, but the roles of the bank and the roles of you are these two roles are switched. So in the mortgage problem, the bank was giving you the money and you were paying the bank back at equal intervals. So here the situation is reversed. You are giving the financial institution like the CPF board a lump sum amount of money at the beginning, and then the CPF board gives you back at a fixed amount at the end of every month at regular intervals. Okay, and indeed the same mathematics will apply. So this is again going back to our previous principle, where the basic principle that we discussed, that there are only certain very fundamental or basic ideas in all these kinds of applications of mathematics in real life, and once you understand those, the same mathematics, the same basic principles will apply to different situations. Okay. So there are two crucial differences, however, from the situation of the mortgage and from the situation of the CPF. So in the situation of the mortgage, the bank determines. The bank gives you the lump sum money at the beginning, and the bank determines the interest rate. in the case of the CPF, you give the CPF board a lump sum amount of money at the beginning, but the interest rate is decided by the CPF board. So this is one difference. And the other difference is that when you take a loan or a mortgage from a bank, then the repayment lasts for a fixed amount of time. For example, in the last example problem, we saw that the repayment lasted for 25 years. Here, in the case of the CPF board, the repayment lasts for the rest of your life. Okay? So there is no time limit. Okay? So the CPF board has to take that into account when it decides that. Let us so after understanding these basic differences between the mortgage situation and the CPF situation, let us go ahead with the computations of the mathematics for the CPF problem. So in the CPF, in the case of the CPF, there are two things to be determined. So since the mathematics is going to be the same, the monthly payment. So in the case of the previous example, so if you use the formula from the previous example, let us take this one. So there in the previous example, C was the amount of money originally taken as loan, alpha was the monthly interest rate, N was the number of years, and R was the monthly payment, rate of monthly payment, everything, right? Here, because of the slight differences of the situation with the mortgage case, it's a slightly more complicated or a slightly trickier situation. First of all, N can last forever. I mean, N will last as long as you live, which is not known for sure at the beginning when you get into the agreement with the CPF, and alpha is going to be decided by the CPF. So so the crucial unknown factor here is N. Okay. So N is, in principle, it's an indeterminate amount of years, it's an indeterminate number of years. It is the number of years between your retirement and between your death, which in principle is not known at the beginning, when at the time of your retirement you enter into the arrangement with the CPF, right? So what the CPF does is that instead of going into the randomness of N, instead what it does is that it uses an estimate for N. The CPF board uses an estimate for how long you will live after your retirement using statistics for the population. So the CPF board has data on the sort of the life expectancies and the details of many individuals, and from this data it arrives at an estimate of an average life expectancy for a citizen after he retires. Okay. So instead of N being a predetermined amount agreed upon between you and the bank in the mortgage case, in the case of the CPF, N is an approximate amount which is of years, approximate number of years, which is used by the CPF often in the form of average life expectancy as an estimate for N, which is the number of years CPF needs to pay you every month as your pension. Okay. For example, if the average life expectancy is 85 and the retirement age is 62, then the CPF so you give the money to CPF, the lump sum at the age of 62, and you survive until 85, So the CPF needs to pay you monthly in order to pay off your money, in order to pay off your invested money every month for these 23 years between 62 and 80, right? So the CPF uses a 23 in this case as an estimate of n, which is the number of years it needs to pay. Okay? So let us take a break of 10 minutes at this point, and when we come back we will continue with the CPF example and also go more into the details of the math of retirement savings. Okay? Hello? Hello? So can everyone hear me? Hello? Hello? Can all of you hear me? Okay, so let us continue with the lecture. So, before the break, we were discussing about investing money with the CPF and getting a fixed amount of monthly pension. And as we already noticed that the situation is very similar or symmetric to the situation when a bank gives you money as a loan, or when you take a debt from a bank, and then it's a bank which gives you a lump sum amount of money at the beginning of a period, and then you pay the bank certain fixed monthly amounts over a large number of months in order to pay the debt off. Similarly, for the CPF, you give the CPF board a fixed amount of money, a lump sum money, usually at the time of your retirement, and then the CPF board gives you back this money in terms of monthly installments, which is your monthly pension for the rest of your life. So, and we discussed that a crucial difference between the situation where you take a loan from a bank and the situation where you invest money with the CPF. One crucial difference is that the CPF needs to pay you for every month for the rest of your life, and at the outset, when you invest the money with the CPF, it doesn't know how long you are going to live, so that the CPF board does not know exactly for how many exact number of months it needs to pay you back. However, as we already discussed before the break, the CPF, instead of this unknown variable n, which is the number of years you live after your retirement, the CPF board usually uses an estimate for n, which is usually the average life expectancy minus your retirement age, okay, as a period, as a number of years it needs to pay you every month. Once this is settled, then the CPF board also needs to decide an annual interest rate it is going to pay you. So this formula is in terms of the monthly interest rate, but you can also write it in terms of the annual interest rate like this. So the CPF board needs to come up with an annual interest rate, and the CPF board, what it does is that you invest the money with this kind of a financial institution, and what it does is that it invests this money instead in various places like the market, and it gets returns from there, and it's from these funds that it pays. So the board analyzes its various investment options, and in order to see what kind of annual interest rate I or the monthly interest rate alpha we can afford to pay. Once it has fixed this monthly interest rate alpha or annual interest rate I, then all the quantities here are fixed. C is the money you give the CPF board at the point of your retirement. Alpha is what the CPF board determines by analyzing in various investments, and N is the number of years that the CPF board estimates you will live by using measures of average life expectancy. So then it uses this formula and crunches the numbers and comes up with your monthly pension. Okay. So here is an example of using these kind of ideas in order to boost your retirement savings or retirement income. So on your retirement, you have a lump sum of $200,000 to provide you an income until you die. So of course you are going to invest it somewhere. So the CPF, so you invest it with the CPF board, and the board estimates that you will live for 20 extra years. So in the previous slide we saw an example of 23 extra years, but for calculation purposes it's easier to do 20 years. So let's do 20 years here. So suppose the board estimates using measures of average life expectancy that you will live for 20 extra years, and it also looks at its investments and decides that after all its expenses and payouts, it can earn 4% annually on the capital that you give. So what is the amount you would expect to receive at the end of each month? So let us do the yoga and use the formulas that we have just learned in the last few slides. So in the last slide, this was the formula. So C is the total amount of money you invest with the CPF board, so it's 200,000. I is the annual interest rate, so I is 4%, but in these formulas you should always use the fraction form, so you should always use the interest rates in the fractional form. So instead of 4%, you should write it as 4 over 100, so 0.04. And N is 20 years. So in order to use this formula, whichever one you use, you have to determine alpha, which is the monthly interest rate. And the monthly interest rate alpha, again, we find using our basic equation, which is 1 plus alpha to the 12 is 1 plus I. Okay. So now we plug in the value of I, which is 0.04, and crunch the numbers and calculate the value of alpha, which is 0.0032737. Okay. So this is just some number which comes up from your calculator. Okay, so now let's see where we stand with respect to this formula. C we know, N we know, and alpha we just calculate. So let's just plug that in and get the monthly payment that you can receive from the CPF board to be $1,204.4. Okay. Any questions? Okay. So here is another example, which is about savings plans. So suppose we have two twins, let's say two girls, Anne and Beth, and so it's this example will sort of indicate to you what kind of strategies are better to take in terms of retirement savings. And actually at the end of the lecture, hopefully we will come to a stage where using basic mathematics like we have been doing in this lecture and the previous lecture, we will be able to justify some of the commonly held wisdoms regarding retirement savings. So Anne saves $A at the beginning of each year for 40 years. Beth starts 20 years later and saves $B each year for 20 years. In order for Beth to have the same amount of retirement savings as Anne when they retire in 40 years' time, how much more must Beth save, assuming that their savings grow at the same annual rate, I equal to 3%. So basically, what is happening is that there are certain common schemes where you can invest your money so that your savings grow. So that common rate of growth of savings is 3%, let's say, for the example of this problem. But the point is that Anne is saving $A for a much longer period, for 40 years, and Beth starts 20 years later, so she saves only for 20 years. So of course Beth will need to sort of save a much bigger amount of money every year in order to catch up with Anne, so that at the point of retirement they have the same amount of retirement savings, although Anne has saved for 20 years longer. She has started. Okay? So the question is, of course we know for sure at the very outset that Beth needs to save more per year. The question is how much. Okay? So that's the question we are going to answer. So suppose Yk denotes the amount of money Anne has at the end of year k. Then she starts from 0, so that is at year 0. So no time has passed, she has saved it. At the beginning of the first year, she saves $A, and she invests it so that the savings inflate by a certain amount. at the end of the first year. So by how much does it inflate? The annual interest rate is 3%. So at the end of the first year, so N's saving of $A at the beginning of the year has received this interest payment for 1 year. So at the end of the first year, it grows, it becomes inflated by a factor of 1 plus I, right? That's what annual interest rate is all about. So this is the amount of money which N has at the end of the first year. After the first year, the second year begins and N saves again $A at the beginning of the second year. So now she puts into the bank. Of course, the bank has her previous Y1 dollars, but she puts her additional $A of savings. So she starts the second year with Y1 plus A dollars of savings, and because of the annual interest rate, at the end of the second year, this Y1 plus A dollars becomes inflated by a factor of 1 plus I to Y1 plus A times 1 plus I dollars. Okay? And as in the case of the mortgage example, it is beneficial in these cases to first substitute Y1 from the previous equation and then expand everything out as powers of 1 plus I. So Y1 plus A times 1 plus I equal to A times 1 plus I plus A times 1 plus I, and let us multiply this out. So this is A times 1 plus I squared plus A times 1 plus I, okay, as we have here. So this is Y2, the amount she has in the bank after the end of the second year. At the beginning of the third year, she starts with what she had at the end of the second year and puts in additional $A. So she starts the third year with Y2 plus A, and at the end of the third year, because of the interest accumulation, this amount gets inflated by a factor of 1 plus I to Y2 plus A times 1 plus I. So again, let us play the same game and substitute the value of Y2 from the previous equation and then multiply it out, and you will see that you get this kind of series in 1 plus I. So you see, this is a recurring theme. Whenever you do this kind of compound interest problems and accumulation of capital, you will see that that because of the nature in which compound interest accumulates, you are going to get this kind of series sum of things. Okay? As we have here, you have A times 1 plus I cubed plus 1 plus I squared plus 1 plus I. So it's a series in 1 plus I. It's a geometric series in 1 plus I. Okay? And then we can use the formula for summation of geometric series. So this is 1 plus I to the K to the J, where J is between 1 and 3. So you can write this, you can take a factor of 1 plus I common. So this is 1 plus I times summation J equal to 0 to 2 1 plus I to the J, right, because you have just taken out one factor of 1 plus I common, and you get something like this. So the formula for Yk is actually going to be very similar, as you can already guess from here. It's going to be A times 1 plus I to the power all the way from J equal to 1 to J equal to K. You notice that the biggest power is the same as the index. So Yk is A times 1 plus I to the power all the way from 1 up to K. Okay? And now we will want to simplify this, the sum of this geometric series for computational purposes. And again, what you do is that you take one factor of 1 plus I common, because it's exactly like this. So you can take a factor of 1 plus I common, and then you are left with exactly summation J equal to 0 to K k minus 1 x to the j, where x equal to 1 plus I. Okay. So this is, in other words, this is a times 1 plus I times summation j equal to 0 to k minus 1, or you can call it L equal to 0 to k minus 1, 1 plus I to the L. Okay, just by taking a constant. And then, so you have this sum, and this sum you can simplify using this formula for geometric series. So we notice that this is 1 minus x to the k over 1 minus x. So you apply this here. So this is so here this is going to be 1 minus 1 plus I to the k by 1 minus 1 plus I, and you can simplify this as 1 minus 1 plus I to the k divided by minus I, but you can transfer this negative sign upstairs so that it becomes 1 plus I to the k minus 1 divided by I. Okay? Okay? Here? So now we are ready for our punchline. So after 40 years of this savings, N has Y40, which is a starting amount, times 1 plus I is 3%, so it's 3 over 100, so it's 0.03. So 1 plus I is 1 plus 0.03, so 1.03, and 1.03 to the 40, because k for n is 40 years, minus 1 over 1. Okay. What does Beth have? Beth has, at the end of the same period, B, because she is saving the amount of money at the beginning of every year, times the same calculation repeated for k equal to 40, right? K equal to 20 years instead of 40. So for B, you can use the same formula with A replaced by B, and for the savings of B, for the savings of Beth, you can use the same formula as you did for N, except you have to replace A, which is the amount saved per year, by B, which is what Beth saves per year, and K equal to 20 years instead of 40, because that's the period of time which Beth saved in. So once you do that, you get the period of, you get the amount of money for Anne and Beth, and you want to know how much more Beth should save every year so that she has the same amount of money as Anne as a retirement savings at the end of this time period. So these two quantities have to be equal. This is the amount of money which Anne saves, this is the amount of money which Beth saves. So if these two amounts of money have to be equal, then you can cancel the 1.03, you can cancel the 0.03. So all that you have is a ratio of A and B to be equal to 1.03 to the 40 minus 1 divided by 1.03 to the 20. Okay? And you can use, so this is a numerical value, you can calculate this using your calculator, and you will get approximately a factor of 3. So in other words, just because Beth starts saving 20 years later and saves for half the time which N does, she has to save 3 times as much as N every year. Okay? So this justifies the commonly held wisdom that start your retirement savings early. Okay? Any questions? Any questions? Questions? Okay, so if there are no further questions, we will end here today, and we will continue with money and personal finances